Hey guys, it's Mr. Sheeline here. I'm just going to be walking through a couple of these multiple choice questions like I told you I would. So I just want to look over a couple of them because I noticed that when I was going through this again, I was like, there's some of these that maybe I didn't use the right kind of language to really nail home what's going on. So let's see. Look in here because we start with the multiple choice questions at number 9. So here's one, number 12. So number 12 we really haven't talked about, and something that really we should have. So it says here, so in order for a rocket ship in deep space, far from any other objects, to move in a straight line with a constant speed, it must exert a net force that is what? So this is a concept that we haven't really talked about a whole lot. I may have made some mentions around it, but arguably I haven't directly told you about it. So when we think about this particular example, we have a rocket ship that's just kind of floating off in space. Okay, so here's our rocket ship. It's floating off in space. Okay, and the question is asking us, what's the force we have to put on it in order for it to continue to move at a constant velocity? So when we're on Earth, we want to think of, well, we have to continually provide a force in order to move something. So if we want to, let's say, pull a wagon. So if we've got a younger sibling in the back of a little red wagon behind us, in order for us to move that wagon at a constant velocity, we have to maintain a particular net force, right? We have to continually provide a net force that's, like, say, in the direction of the motion, constantly, because the whole time we're working against a couple things. We're working against gravity, we're working against friction, maybe a little bit of air resistance, and so in order for us to continue to maintain a constant velocity, we have to maintain a particular force. But out in space, in order for something to maintain a straight line and to maintain a constant speed, it must exert what kind of net force? Is it going to be proportionate to the mass, the weight, the velocity? Is it going to be 0, or is it going to be proportionate to its displacement? So, well, we can say that this is definitely a no-go. It doesn't matter how far we go. Displacement doesn't matter when it comes to exerting a particular force in this case. Is it going to be proportional to the velocity? Well, that doesn't make really any sense, because we really haven't talked about it all, how velocity really has anything to do with a net force. We have talked about weight, and we have talked about mass. Now the weight, no, because we're out in space. Okay. And arguably, you could even cross off mass. And the answer is 0. So why is it 0? Well, remember, when you're out in space, you have no other unbalanced external forces affecting it. You don't have gravity. You don't have friction that you have to constantly be fighting against. That's why on Earth, if we're pulling a wagon, if we're pushing the wagon, whatever we're doing, we have to continually push it because we're working against friction. We're constantly working against gravity. And so that's why we have to constantly maintain a force on Earth. But if we're out in space, there are no forces to deal with. So as long as you've got a first initial force to get your object moving in a particular direction at a particular speed in a particular, I guess I already said direction, all you need is that initial force. And then after that, it's just going to keep floating and floating and floating. So in order for it to maintain constant velocity, we don't have to exert a force. Net force is just 0. Okay? Which is kind of a tricky thing to think about, okay? And that's why it's important to remember that there's a distinction between how we move objects on Earth versus how we move objects out in space. Okay, because remember, out in space, there's like virtually no external forces that are affecting our objects in motion. Okay. So another one that I wanted to look at, let's see, there was one other one that I was like, ooh, let's see. It might have been 16. Spacecraft travels. But I'm going to read 15. A spacecraft travels at a constant velocity. Okay. I think you'll be able to figure out number 15 after we just went through number 12. Well, let's take a look at number... If a boy rides a bicycle at a constant velocity, which of the following is true about the net force? Oh, I know which one. I know which one I wanted to look at, because you'll be able to get those. It was number 20. So this is not language I used here, really at all. In fact, I've really used language again, that expands a little bit past what they're asking for in this question. So in number 20, the question is, the acceleration of an object is proportional to, and then we have to make the selection out of these 5 things. Okay, so what we should be thinking about here is that this is just simply asking about more or less Newton's second law. Okay, Newton's second law. Okay, and we know in Newton's second law, F is equal to m times a. What really Newton was concerned about this, he was concerned about the acceleration of an object. How much force do we put in by, or per the mass that the object has. So the acceleration of an object is proportional to what? Now, in Newton's second law, the way that we've described it is that Newton's second law is how quickly can we change an object's velocity, what's its acceleration, per the amount of force that we put on it, and also the mass it has. So we've always talked about it having 2 things that it's proportional to in somewhat. To a certain degree, or at least I've used language that says like, hey, you have to take into account both force and mass. But the language they use here in this question is like more of like, no, what's the one thing that acceleration is concerned with? And here we can see there's mass and there's also net force acting on it here, because we know that that's really the 2 things that are going to, find our acceleration here. So let's just go through those options then. So they say the net force, position, velocity, mass, displacement. Well, we know we can get rid of displacement. Remember, it doesn't matter how far we go. That's not what force, acceleration, or mass is terribly concerned with. Acceleration may be concerned with it if we don't know how quickly we're changing our velocity, but that's something completely different that we just haven't really gotten into. Is it the position? No, again, that's the same thing. Like position and displacement are really the same answer. Again, it doesn't matter how much we change our position. It matters about the rate in which we change our position. That's our acceleration. Well, at least the rate in how much that rate changes is our acceleration. Because velocity is the rate in which our position changes. So is it going to be velocity? Well, no, not really, because we don't directly use velocity in this equation. Obviously, velocity has something to do with acceleration. So then it leaves up to net force acting on it and mass. And we really have to ask, which one is it? Is it going to be mass? Not really. And the reason why it's not going to be mass is because the reason why it's not mass, how to put it, and this is why I don't really like this question, because acceleration takes into account both things. I'm trying to figure out how to explain it to you guys on the spot. I guess we'll say that it's proportional to the force. It's proportional to the force. I guess if we look at the equation mathematically, we're saying that acceleration is equal to the force per the mass. So it's proportional to how much force we initially put into it. And then it's that the mass then comes in and the mass is like, hey, like, I've always been here. You've always known that I have this amount of mass. If you want it to go this quick, you've got to put this kind of force. So I guess that's the best way I could explain it. The reason why acceleration is proportional to the force is because, again, we already know this, or we should already know this, and the idea is that if we want it to move this quick, we have to know how much of this to put in. So I guess that's the reason why the answer here is going to be A and not going to be mass. Because and you can think of it in this way too, is that we're dividing mass, we're taking into account how much it is, and so because we're taking into account, we're trying to get rid of it. We're trying to say, get out of here, mass. We don't want you here. We want to know how quickly we can move something, how quickly we can change its velocity per the amount of force that we put on it. So get out of here. We're getting rid of you. Okay, kind of a strange way to describe it, but that's the best way I can describe it. So, but that's pretty much it. Those are the two questions I really kind of wanted to walk you guys through. So there's 2 3 points that you guys can earn on here. Last thing I'll plug in here is please don't skip this extra credit. It's actually probably going to be easier for some of you than you actually think. I'll just tell you that the best way I'll give you 2 hints. This is the 2 hints I'll give you. The 2 hints I'll give you is that 1, write out all the variables that are listed here in numbers 1 and 2. List them all out. And then that's hint number 1. Hint number 2 is that there's going to be 2 equations that you should be, or 2 different formula you're going to be using in order to find what the average net force is for both of these objects. And that's all I'll say, because these are decently hefty problems. So if you're able to get 10 extra points, and shoot, man, if you already got like 100% on this, this could bump this extra credit due to the way I grade. You know, I pop in grades for this class. Is that it could alter your grade decently. If you're at like a high B, this could bump you up to an A. I haven't tried that, but I could see it happening. Point being, and I guess I shouldn't have said that. I shouldn't drag you guys along like that, because I don't know for certain if it'll bump your grade up that much, but it can't hurt. I guess that's what I'll say. It can't hurt. So yeah, don't pass up on the extra credit. Definitely take a swing on the extra credit. And that's pretty much it, guys. So if you still have any questions for me, make sure you ask. If not, I'll see you all in the next one.